Hello, everyone. So this is a joint work with Camille, Bourgaux, Rafael, Peñaloza, and Livia, Predoiu. Ontologies have been successfully used for data integration, and there are many benefits for doing so. But when one starts integrating multiple data sets on data sets get very large, there are new challenges that arise. For instance, how reliable is the query result, or how was it produced? How many different ways are there to derive it, and how dependent it is from certain parts of the data. And in order to deal with these questions, provenance semi-rings were introduced in database theory, and they provide a way of representing how and which parts of the data were used. It's nicer to understand this notion with an example. So suppose here that we have a conjunctive query, exists X, Y, where X cites Y and Y is an academic work. And in our data, we have the tuples Philip cites paper ID, which is an academic work, and also Mary cites paper ID. And if we want to see which parts of the data are used and how, the way it is done, as it was first proposed in database theory, was to annotate each tuple with a symbol, here with P, R, and Q. And the provenance polynomial would be R times P plus R times Q. And what does this represent? Well, it represents that we use the tuples Mary cites paper ID, and paper ID is an academic work in a joint way, and that's why we have the times operator here. And also that we have an alternative way of getting this query result, and this is why we have a plus operator in between these two terms. So what we do in this work, we consider the case where we don't just have data, but we also have an ontology. In particular, we consider the ELHr ontology language for constructing our ontologies, and we will annotate the concept inclusions within this ontology. It is worth pointing out that this work is related in terms of the setting with a previous work that Rafael did together with Diego Cavanese, David Elanti, and Bourgaux. And we consider in that work the ontology language ELHr, and we also had mappings in that setting. But what we observed while looking into ELHr is that the problem gets very different because of the different kinds of expressivity that we have in ELHr. So to construct our ontologies, we consider concept inclusions of the form C implies D, where on the left side we have an arbitrary EL concept expression, but on the right side we just have A and exist R. And I will explain in a minute why we consider this syntactic restriction. We also allow in our language role inclusions and range restrictions. So this is an example where we want to give, I want to give an intuition of what we want to derive with our semantics. So suppose that we have the fact that Mary cites paper ID with provenance Q, and Philip cites paper ID with provenance P. And we also have here a concept inclusion, which says that the range of sites is academic work. And this is also annotated with a provenance symbol, which in this case is S. So what we would like here is to derive academic work with these two provenance information, P times S and also Q times S. And the intuition for this is that in order to derive this, we use both the tuple, which has provenance P, together with the concept inclusion, which has provenance S. So this is what we would like to derive. So we would like the provenance information to be combined using what appears to derive a fact. And just to give you a bit more of detail on our semantics, it's similar to the classical case of ELHr, but here we have an additional domain, which is the domain of monomials. And in our semantics, essentially when we consider concept names and role names, we associate, in addition, an element of this domain of monomials. And these monomials, they are taken from the set, an M, and we are going to map them to the same elements in the domain of the monomials if they are equal modulo associativity, commutativity, and idempotency for the times operator. So Q times Q will be equal to Q in our case. So let's first consider that we don't have this extra condition here, because this is closer to what we had in the database setting, and then I will explain why we added this. So suppose here that we have this fact that Mary cites a paper ID with provenance Q, and we also have this concept inclusion that a range of sites is an academic work with provenance S. So in our semantics, we have that Mary, paper ID, and Q are in the extension of sites. So the individual names here I will just map to themselves, but the provenance symbol, I will have this I operator here. And here the semantics of range R is going to be the set of E, elements E with provenance M, such that there is an element of the domain, which is D, and D and E is in the extension of R with provenance M. So just replacing this with our example, we have that paper ID, which is in the range of sites, is going to be in the extension of this concept expression. And our semantics says that if we have a concept inclusion, where we have C implies D annotated with S, and an element is in the extension of C with provenance Q, then it should be in the extension of D with provenance S times Q. So essentially we propagate the provenance information. And in our particular example, we have that paper ID is in the extension of range sites with provenance Q, and it will be in the extension of academic work with provenance Q times S, which is what we wanted, because in order to derive this, we have used both the fact and the concept inclusion. So it will follow this assertion from our semantics. And we also can have Q times S, because our semi-ring is commutative, so it doesn't matter the order. Okay, so this is for commutativity, and now I will explain why we added this condition here for idempotency in the times operator. So suppose we don't have such condition, and we have a new concept inclusion here, which says that if somebody cites an academic work, then this person is a researcher with provenance T. And the semantics says that an element is in the extension of ELHr, here D with provenance M times N, if there is an element in the domain such that D and E with provenance M is in the extension of R, and E is in the extension of C with provenance N. So it's very close to the classical semantics for ELHr, but now we have provenance information, and when we consider a concept expression, we combine this provenance information. So this is replacing with our example, and what will happen in this case is that we have Mary with provenance Q in this extension of sites, and we have this element E, in this case an academic work, the paper ID with provenance S times Q. And our semantics will say that if we have a concept inclusion with some provenance symbol, in this case T, and something is in the extension of C, it will also be in the extension of D, now with the T symbol, which in our case means that if we apply this second concept inclusion, we will be able to entail that Mary is a researcher, and this will be the provenance. Now, this goes against a bit our intuition, because since we have used these three axioms to derive, it will not follow that Mary is a researcher with provenance S times Q times T, and the reason is because Q was used twice. So if we would like to have such entailment, a way to do this is to say that the times operator here is idempotent. So Q times Q will be equal to Q. And then in this case, it will follow that Mary is a researcher with this provenance information, and that's because this is the same as having this. So a similar difficulty arises when one has conjunctions on the left-hand side. And one thing to notice here is that this is a problem that we did not see in ELHr, and that's because in ELHr we don't have this kind of expression. We never combine information in multiple tuples as we have here. Now I would like to talk a bit about this syntactic restriction that we imposed in concept inclusion. So suppose we don't have any such syntactic restriction, and suppose that here in our ontology we have concept inclusions of the form C implies D, where C and D are taken from this grammar rule. So suppose here that we have Mary, and Mary is a researcher with provenance information Q, and we have a concept inclusion here which says that if somebody is a researcher, then this person cites an academic work and is with provenance T. So our semantics will say again, once again, that if we have C implies D with provenance T and something in the extension of C with provenance M, it will be in the extension of D with provenance M times T. Now, replacing this with our example, we have that if Mary is a researcher, then Mary is going to be in the extension of exists cites academic work with provenance Q times T.
Sorry, you have two more minutes.
Okay, so it will follow that we have this assertion that Mary cites academic work with this provenance information. Now the problem is that when we define the extension of exist RC, we have that we simply combine the information of the parts here, R and C. And this means in our example that we may have associated with sites, we have the provenance information Q, or we could have T, because it's commutative, we just require that the product is Q times T, or we could even have Q times T here and just one in the other side, or the other way around. So what does this mean? It means that even though cites academic work Mary is entailed, we have that exist R top Mary is not entailed with any provenance, because we may have multiple models and each model will have a different provenance value, which does not match with our intuition that if we have something that is more specific here, we should be able to entail a more general concept. So that's why we added this syntactic restriction to our language to avoid counterintuitive entailments. And a similar situation happens when we have conjunctions. Again, this is also a problem that did not show up when in a previous work we were looking into the ELHr. So this picture is just to illustrate our impression when we were considering this problem. So initially we had the ELHr and lots of things worked, and when we consider ELHr, the problem got in different ways more complicated. Our main results in this work are essentially complexity results for deriving this our entailments together with provenance information. It can be just a monomial for instance queries, or a polynomial for when we have conjunctive queries. And overall, what we did was to make an investigation for this language, and where we observed that when we have conjunctions and qualified role restrictions, we have a different behavior than we had for the ELHr. And we have complexity results for query languages. When for the instance queries, we used a completion algorithm, and for the conjunctive queries, we made a non-trivial adaptation of the combined approach for ELHr.
So please wrap up.
Yeah. Yes, and then we just looked at this other problem that is in polynomial time. That's it. Thanks.